Right, so since our last two um, lessons were on Newton's first and second laws, you can safely assume this one's going to be on Newton's third law. And before we get into discussing his third law, we need to realize that forces always come in pairs. And what we call an interaction pair is when we have two forces that occur in opposite directions and they have equal magnitude. And what I mean by that is consider these two, um, I don't know, space people on the right. They're on roller skates and they push each other. As you can see, when if one, let's just say the one on the right pushes the one on the left, uh, he pushes the one on the left back, but the one on the left also causes the one on the right to move backwards as well. Just like if you've ever pushed a friend on ice skates, you should notice that not only does your friend move, but you're probably going to cause yourself to move backwards as well. And the reason for this has to do a lot with Newton's third law. Uh, what his third law states is that the force of A on B is equal in magnitude, yet opposite in direction of the force of B on A. So notice how the subscript in that equation underneath shows the force on A, or I'm sorry, the force of A on B, the force of B on A. They're on opposite objects. When we talk about interaction pairs always have to be on different objects. So when you think of holding a book in your hand, for instance, the weight of the book, you might want to think the weight of the book uh, is an interaction pair with the normal force of your hand on the book. And that's very tempting to think that way because the two forces are opposite in direction and equal in magnitude. However, interaction forces must be on different objects. So both the weight and the normal force are on the book, so they can't be interaction pairs. What the interaction pairs in that case actually are the force of the book on your hand would be an interaction pair with the force of your hand on the book. You know that the book exerts a force on your hand when you exert a force on the book, because you obviously have to put effort forth to keep the book in the air. Otherwise, there would be no force. You feel it in your muscles. Likewise, the force of gravity on the book, the interaction pair with the force of gravity on the book is the force that the book puts on the earth, which might sound crazy that that the book actually pulls the earth with a gravitational force, but it's true. Every object in the universe exerts a gravitational force on every other object in the universe. The reason you don't notice it is because, as we'll see in our example problem on the next page, Earth has such a huge mass that, if you remember, according to Newton's second law, that huge mass with the little force the book is going to exert on the Earth is going to create virtually no acceleration whatsoever. So just thinking of this soccer ball on the table on Earth, we can view all sorts of interaction pairs. You have the specifically on the ball, we have the table exerting a normal force up on the ball. The interaction pair would be the ball's force on the table. When you have the earth pulling on the ball, its weight, the interaction force to the weight is the ball pulling back on the earth. You have to remember that those interaction forces have to occur on different objects. We could even go as far to say as the ball exerts a gravitational force on the table, and then the table exerts a gravitational force back on the ball. But those are so small that they're essentially negligible. So if we look at this example, when a softball with a mass of 0.18 kilograms is dropped, its acceleration towards Earth is equal to g. What is the force on Earth due to the ball, and what is Earth's resulting acceleration? Let's see here. So we know the softball has a mass of 0.18 kilograms. I'll call that M sub S, S standing for softball. And we know that the acceleration is g, or 9.8 meters per second squared. We know that the Earth is exerting that force on the softball that gives it that acceleration. So we know we have the force of the gravity on the softball. We know that that is a interaction pair, a Newton's third law pair, if you want to call it. Because if the Earth pulls on the ball with that force, the ball is going to pull up on the Earth with that same force, that force of gravity that we referred to. So because these forces are going to be equal and opposite, we can say, well, let's figure out the force of gravity is equal to the mass of the softball times the acceleration of the softball, which is again 9.8. And we can say the mass of the softball is 0.18 times 9.8. So the force that Earth exerts on that softball is 1.8 newtons. So that means the ball also exerts a 1.8 Newton force on the Earth. The two different systems here. So one thing you would have to look up to figure out the acceleration that the ball exerts on Earth is the mass of the Earth. And we know that the mass of the Earth is 6.0 times 10 to the 24th kilograms. Obviously a huge mass. So if we look at acceleration, we know that it's the net force over the mass of the object. The force exerted on Earth is 1.8 newtons by the ball. The mass of the Earth is 6.0 times 10 to the 24th kilograms. If we divide those two numbers, the acceleration of Earth is going to be 3 times 10 to the negative 25th meters per second squared. I guess 3.0 to keep our sig figs straight there, which is a very small acceleration. It's 0.0 with 25 zeros, 3 meters per second squared, which is exceptionally small. And that's why the Earth is not going to show a visible effect. Not only that, but you also think on the other side of the world, everything in China exerting a force. If we assume we're in America, everything in China is exerting a force the other way, so all the accelerations around the Earth are going to cancel one another out. So as unrealistic as it sounds that we exert a force on Earth, especially like when we're walking, what's causing us to walk is we're actually pushing the Earth away from us, so the Earth pushes back. So that might seem unrealistic, but when you look at the numbers, it causes it to make a lot more sense because that acceleration is so small, it's not noticeable. So let's talk about, we referred to this in class a little bit, talking about force diagrams, but just the forces of ropes and strings. We call any force that is exerted through a rope by another object, or through a string, or through a chain, or anything that transmits a force, we call that tension. And in this class, to simplify things, we're going to usually consider most of these ropes and strings to have no mass. But you can kind of think as the string or the rope is a bunch of little particles pulling on the another. If that gets transmitted the whole way down, each particle pulls on the other one with the same amount of force. That tension gets transferred through the rope, and it's the same everywhere in the rope because all the forces cancel out. It's an equilibrium. So what this is saying is you have the bucket's weight pulling down with the force of gravity, and so the bottom part of this rope, to keep that bucket in equilibrium, has to pull up with that same amount of force, Fg. We call that Ft for tension. And then you think of the top of the rope. The top of the rope's got to pull on the bottom part of the rope. Since the rope's in equilibrium, we know that the force that the rope pulls up on the bottom part has to equal the force that the weight pulls down from the bucket. So since everything is in equilibrium, those cancel out. That's why the tension's the same everywhere in the string. And if we think of a tug of war battle, it might seem like if you have each team pulling on the rope with 500 newtons, it might seem like the tension would double in the rope. That you would have 1,000 newtons of tension in the rope, but that's not true. If you think about it, this team is pulling on the rope at 500 newtons, so that means the rope is also pulling on this team at 500 newtons. So if you just kind of think about replacing this whole team with a stationary object like a wall or a pole, if you remember Newton's third law, that pole is going to pull back with the same amount of force as the other team pulls on the rope, because let's say they're in a stalemate, they're in equilibrium. So if it still doesn't make sense why the tension in the rope is only 500 due to Newton's third law, think about if we divided that rope in half. If you were just holding the rope in the middle, you would feel 500 newtons from each pulling team, depending on which side of the rope you were pulling. Or if you put a spring scale on that rope, if the team pulled with 500 newtons, the spring scale where the other team stands would pull with 500 newtons. It would show 500 newtons. So that 500 newtons is going to be the tension in the rope, since it's the same throughout. It doesn't matter if you have another team pulling on the other side with 500 newtons, or if you have a tree on the other side pulling with 500 newtons. The force of tension in that rope is going to equal the pull from one side. Remember, every interaction pair of forces is equal. Even if you think of a force of a car hitting a bug, you might want to say the car puts a lot more force on the bug than the bug puts back on the car. But that's not true. The bug hits the car with as much force as the car hits the bug. It just so happens that energy goes into deforming the bug, but the same rate, and the bug just doesn't exert as much of an acceleration back on the car as the car exerts on the bug. So but you have to remember, anytime contact forces or any other forces are made with one another, the two interaction forces have to equal one another. So let's look at this example. We have a 50-kilogram bucket being lifted by a rope. The rope will not break if the tension is 525 newtons or less. The bucket started at rest, and after being lifted 3 meters, it is moving at 3 meters per second.
the acceleration is constant, is the rope in danger of breaking?